All right, we're recording. It seems like not everybody here, but a lot of you, some of you are not attending at all. So I'm gonna start taking pictures of my screen. So when you fight with me over a grade, I'll tell you you didn't care to come to class. There. Okay? So I'm gonna treat you like undergrad anymore. All right. Because it seems like after I made several announcements about the homework, some people are still emailing me that indicated to me they never come to class and they're not watching the videos. So that's really bad. And anyway, any questions? Are there any questions? All right. We're going to continue with the material. All right. Well, you know what? Keep reading in the book, and I discussed the complex roots. Okay. Further on, I mean, not further on, the complex roots are being discussed. So just read the discussion and do the homework if this is what you're talking about. Okay. I mean, what I meant, use the theorem because from that theorem, you can get to the complex root. There's nothing new. Okay. Um, so last time we defined so we were looking at x prime equal ax, x of t naught equal x naught. And that is 3.2.14, we refer to it. So we wanted to find e to the a t minus t naught. And this is the exponential matrix. So one way you can find the fundamental matrix solution phi of t, and then e to the a t minus t naught is phi of t, phi inverse of t naught. Okay? So basically here, this is only when a is constant. When a by a is an n by n constant matrix. So this is one way you can find, or two, last time, a, if a is diagonal, then look at previous example. And what I mean by that, I'll flip the board and I'll show you what I mean by that. So we did an example that discuss this. But you see, this one is a part of this one because it's the same as finding the eigenvalues, eigenvector. But this one was a direct use of this one using Maclaurin series of the exponential function. Okay? All right, any questions? So, and the example I'm referring to is this one here, when we found, I think A was 3, 0, 0 minus 1. So you just keep raising an, and then you will write. So we did this example last time. So that is very simple due to this this way. All right. So any questions? Okay, today we're gonna look at a very important theorem. It seems like I'm not gonna do the proof of it, but I'd rather go over an example to illustrate it. All right. So the next example, a theorem, this is theorem 3.2.14. And this is called Potter algorithm. This is on page 87. I'm going to ask you, I will ask you to do the proof. Suppose A is an n by n constant matrix, okay, with eigenvalues lambda 1, lambda 2, lambda n, with which may come in any order or multiplicity. In any order or multiplicity. Okay? Suppose mu1 of t, mu2 of t, mu n of t satisfy the corresponding initial value problems mu1 prime equal lambda 1 in mu1 with mu1 of 0 equal 1 and mu j equal lambda j mu j plus mu j minus 1 with mu j of 0 equals 0 for j equal 2, 3 to n. And we're going to call this is 3.236. Okay? So this is let the matrices P0, P1, Pn be defined by P0 equal I, and Pj is the product k equal 1 to j a minus lambda ki for j equal 1 to n, and this is 3.2737. Then e to the at is j equals 0 to n minus 1 mu j plus 1 of t pj, okay? And this is 3.2.38. So there is the theorem. So that is regardless. So this theorem, take care of all cases, whether they're diagonal or whether finding the fundamental matrix or whatever. You can use this one directly. Okay?
Just to clarify here,
Yes.
are the mu's, are those scalars or are those vectors? I'm not
These
clear.
are function. No, these are function. Mu1 prime equal lambda 1 mu1.
Ah, okay. I missed that. Thank you.
No, that's fine. Mu j, so these are functions based on the eigenvalues, okay? And you see where they enter. Now these are vectors. These are polynomials, okay? So e to the at is a polynomial, right? Not polynomial, it's a matrix. E to the at is a matrix. And the pj are matrices, and this is a scalar function. So you need to solve each one of those and then stick them in here. And then you need to calculate the pj from here, a minus lambda ki. You see what I mean? And k equal 1 to j. All right? So take a good look at the theorem before. I'm going to ask you to read the proof. Read the proof. Okay, it's in the book. Any questions? So then recall that in this case, remark then the solution of 3.214, which is this one here, x prime equal ax, x d naught equal x naught, is x of t equal e to the a t minus t naught times x naught. And this is n by 1 vector. Okay? Then this is the solution. After we compute e to the a t minus t naught. I do want to, yeah, okay? So if you know e to the at, to compute e to the at minus t naught, you replace t with t minus t naught. T naught could be given either 0, 1, 2, 1/2, or whatsoever. All right? So this is called the Puzzle algorithm, and it's a very important theorem or algorithm on how to find exponential matrices. Okay? All right. Any questions? And today is my birthday. I'm 66 years old today, believe it or not. All right. Any questions? Okay, let me see. Somebody commented. Does it only work with a constant? Yes, it's only constant matrices. Only constant matrices. Don't you dare compute the eigenvalue and eigenvector of a non-constant matrix and build the fundamental matrix solution. It does not work that way. Okay? All this is about constant matrices, and this is why I had a special section in the book when A is constant. Okay? So everything we've been talking about, we define the fundamental matrix for the general matrices, whether A is constant or not. But remember, we were only able to find the fundamental matrix through the eigenvalue, eigenvector when A is constant matrix, okay? All right? Including this theorem. All right, any questions? Okay, so let's do an example. You see, A is an n by n constant matrix. All right. So the best thing to do is an example in the book. So this is example 3.8. So we have x prime equal to 2, 2 minus 1, 2 minus 1, 2 minus 1, 2, 2, x1, x2, x3, and I have x of 0 equal x0, that is equal to 1 minus 1, 2. Okay, why don't you go ahead and compute the eigenvalues for a second. Take a few minutes and do it. Okay? All right. Well, I'm gonna just, since I'm allowing you to use application to you find the eigenvalues, I'm not gonna waste time on it. So eigenvalues is lambda 1 equal 3, lambda 2 equal to 3, and lambda 3 equal minus 3. Okay? All right? All right. Now it does not matter how you reorder them. The order should not matter. The final example, the final answer, after you apply the initial factor, initial conditions, is the same for any order of lambda 1, lambda 2, lambda 3. Okay? So what I said is the order should not matter. The final answer after you apply the initial condition is the same for any order of lambda 1, lambda 2, lambda 3. Okay? All right. Any questions? All right, so now we're gonna use 3.237. All right. So let's use P0 equal I and Pj equal to K equal 1 to J. Okay. What is it says? A minus lambda Ki. Okay. So, and here J is 1 and 2 because so P0 is I is 1 0 0 0 1 0 0 0 1. A P1 is A minus lambda 1 I. And if you do that, will be A minus 3I, correct? You know what A is, and you know what I is. So that will be minus 1, 2 minus 1, minus 3I will be 2, minus 4, 2 will be minus 1, 2, minus 1. Okay? If you want to think about it. Okay? and a P2 equal to the product K equal 1 to 2 of A minus lambda Ki, and that is A minus lambda 1I times A minus lambda 2I. Okay? And that is A minus 3I times A minus 3I, and that is A minus 3I. You square it. You know how to square the matrix. You multiply it by each other twice. Okay? So basically, it is this matrix here. It is minus 1, 2, minus 1, 2 minus 4, 2, minus 1, 2 minus 1 times minus 1, 2 minus 1, 2 minus 4, 2, minus 1, 2 minus 1. Okay? Then you multiply this matrix together. All right. So what is left? I will flip the board. All right. So you see the theorem is we need to compute these. We did. Then now we need to compute the mu j plus 1, mu 1, mu 2, and mu 3. That's what we need to compute next. So we're going to have mu 1 prime equal lambda 1 mu 1 of 0 equal 1. This is what the formula says. Okay? So I'm going to go back to that. So we need to solve the mu 1 prime equal to lambda 1, 3 mu 1. And that means mu 1 of t equals c e to the 3t. So we have 1 equals c, implies c is 1, and mu 1 of t is e to the 3t. Okay? So that is mu 1 of t. All right? Any questions? Okay. Next, we need to find. Now, you saw how we computed these matrices. I'm not going to worry about them too much because you know how to compute them and put them in the final formula. All right. So, what do we have? Mu2 prime of t equal to, let's take a look here. Lambda 1, lambda 2 mu2, okay? So is lambda 2 mu2 plus mu1 of t mu2 of 0 equals 0. So all you have to do is put j equal to 2. to get mu2. That would be lambda 2 mu2 plus mu 2 minus 1 would be mu1. Okay? And then mu2 of 0 is 0. All right. Now, what is mu1? So this is mu2 prime of t equal 3 mu2 of t plus e to the 3t. Okay? Go ahead, take a minute, see how you will solve this problem. I'm going to give you a few minutes. To solve this, so it's going to be mu2 prime minus 3 mu2 equal e to the 3t. So this is the same as d of dt of e to the minus 3t mu2 equal e to the minus 3t times e to the 3t, that is 1. This is the integrating factor for this equation. Okay? All right. So integrate. If you integrate, you get e to the minus 3t mu2 equal t plus c1, or in u2 is t e to the 3t plus c1 e to the 3t. Now 0 equal in u2 of 0, that is c1. So mu2 of t is c1 is 0, it's t e to the 3t. Okay? Take a look at what I did. Any questions? All right. Now, let's take a look at j equal to 3. So you get 3, and I'm talking about here. J equal to 3 will be lambda 3 mu 3. What is lambda 3? Minus 3 mu 3 plus mu 2. So mu 3 is minus 3 mu 3 plus t e to the 3t. That is this one. So go ahead and solve it. Let's see what you get. And you have mu 3 of 0 equals 0. All right. So I'm going to erase this and try to do it. So again, so it's mu 3 plus 3 mu 3 equal t e to the 3t. All right. So the integrating factor is e to the 3t equal t e to the 6t. See what happened? So integrating, you get e to the 3t mu 3 equal t e to the 6t plus some function c2. Now we need to integrate this one. Well, we're going to do this integration by parts. We're going to take u, this is u equal t, and dv is e to the 6t. So du is dt, and v is e to the 6t over 6. So t e to the 6t dt is uv, will be t e to the 6t over 6, okay, minus v du, minus v is e to the 6t over 6 dt, and that is t e to the 6t over 6 minus e to the 6t over 36 plus c3. C2, we said C2. All right. So we have e to the 3t mu 3 equal to t e to the 6t over 6 minus e to the 6t over 36 plus c2. Multiply by e to the minus 3t equal t over 6 e to the 3t minus e to the 3t over 36 plus c2 e to the minus 3t. Now apply 0 is a mu 3 of 0. We get 0 equal to 0 minus 1 over 36 plus c2. So c2 is 1 over 36. Okay? With that being said, mu 3 of t is t over 6 e to the 3t minus e to the 3t over 36 plus c2 plus e to the minus 3t over 36. There we go. Okay? So now I have a mu1, mu2, and mu3. All right? Any questions? All right. So, and what is mu1? Mu1 of t is e to the 3t. And mu2 is t e to the 3t. Okay? Now let's write down the solution. Okay? So e to the at is from here is j equals 0 to 3 minus 1 because the matrix is 3 by 3. Mu j plus 1 of t pj. And that is mu1 of t p naught p0 plus mu2 of t p1 plus mu3 of t p2. Now, do we know what the p's are? Of course we do. We already computed them. All right? Remember, the p's we erased. So let's hope I have the final answer in the book. Well, I didn't. Okay. So these are matrices. Okay. So the final solution, the solution is x of t equal e to the at x naught. That is mu1 of t p naught plus mu2 of t p1 plus mu3 of t p2 times what was the initial vectors? The initial vector was 1 minus 1, 2. Okay? Remember, these are matrices. This is a matrix. Scalar matrix, scalar matrix, scalar matrix. Okay? All right. Any questions? What is this? All right.
Just to be clear, you said scalar matrix, scalar matrix, scalar matrix. I think, did you mean function?
Yeah, this is well, function is a scalar still.
Oh, a scalar function. Okay, cool. Yep.
Yeah.
Just make sure I'm.
Yeah. So scalar times a matrix is a matrix, right? Matrix, matrix. Okay.
Yep.
Times a vector, you'll get a vector, right?
Yep.
Because x is a vector, x1, x2, x3, correct? Now, this is hypothetical. What I'm going to write next is dangerous. Let's take x prime equal ax, right? And xt naught equal to, let's say, x4 equal 6, 7, 8. So basically, t naught here is 4. And let's say e to the at is 2 by 2 matrix. E to the 2t, t e to the 2t, 1, 9 e to the t, e to the 2t. Because, all right, I took it to be, all right, so sorry about that. E to the at is, okay, let me take a look for an example in the book so I can use it illustrated better. All right, so let's see when we took I want to illustrate this idea to you carefully because a lot of students get it wrong. It take a lot of years of experience. Let's say we have x prime equal 3, 0, 0 minus 1 times x1, x2. And let's say I have x of 4 equal minus 1 and 3. I don't want the 3. 7. And I don't want this minus 1. Minus 8. I want everything to be different. So in this case, e to the at is 3 to power t, 0, 0, minus 1 to power t. That's what it is. Okay? Sorry, no, e to the minus t. Okay? E to the minus t. Now the solution, x.
Hi, Professor.
Yeah.
I think that should be e to the 3t, not
Yes.
3 to the t.
Yes.
Cool.
E to the 3. Thank you. All right. Then x is e to the a t minus 4 times x of 4. So this is e to the 3t minus 4, 0, 0, e to the minus t minus 4 times minus 8, 7. You see how you write the solution? Okay? Be careful. Not always T naught is 0. But you compute e to the at and then include T naught in the answer, in the final answer, okay? And remember, finding mu1, mu2, mu3, their initial condition does not depend on this. Their initial condition is always at 0. Is that clear? Okay? All right. So there are more examples in the book if you want to look at them. Okay?
So, can I ask a question regarding?
Sure.
I guess I'm just trying to figure out why we would use this algorithm as opposed to the definition of the matrix exponential. And my guess is that
What? Sorry. Let me stop you here. What is the definition of the exponential?
I'm looking for the equation number here. It's the Taylor series expansion is what it is, wherever.
Oh, and do you really think you can find an if a is not diagonal?
That was going to be my point is I'm guessing you want to use this algorithm because at some point you could get a matrix that doesn't a to the n does not converge.
I mean, last time before I finished my lecture, I took a to be diagonal because, as I said, easy way out for then. I did not want to go through this theorem yet. Okay.
Right.
Yeah. But even if you use this theorem for the other diagonal matrix, of course, you're going to get the same answer, right? If you use this theorem for the diagonal matrix. But you cannot, not every matrix is diagonal unless you want to, you go through the Jordanian canonical form, which is I don't recommend. Okay?
So my hunch, and I think you just answered this, was going to be this algorithm is going to give you something you can work with regardless of the form of A.
Exactly. And remember, and regardless of the multiplicity of the eigenvalue, remember when the eigenvalues were real, we found then depend on if we find linearly independent eigenvectors or not, right? If not, then you have to go through the generalized eigenvectors as you did on your exam, didn't you?
Right.
Yeah. So you have to use the generalized eigenvectors. So on your exam, you can take the same problem and use this algorithm on it and it will be much easier. How's that?
Good to know. Cool. This is a short answer. This is a generalization. So
This is a general of everything you've seen. As
right.
long as A is, what is the punchline here? A is
a constant matrix.
Constant matrix, okay? All right. All right. Thanks, Chris. Any other questions? Okay, so let me see where I am. Let me get my notes in order here. Okay, just stay with me for a second. All right. Okay, let's end the lecture with this, the non-homogeneous system. All right. Okay, so now we are in section 3.3. And this is called the x prime equal ATX plus G of T. Now, okay, so when did we make the distinction between A being constant and A is not constant? When we found the fundamental matrix or the exponential matrix, correct? Now, we're going to write a general formula that will work whether A is constant or A is a function. Just a minute. Oh my God, that is very good. Yeah, it is excellent.
Now that's purple. Like I don't want to go and get stocks, you know, everything, but
Well, they said if you're gonna change what? The road. Oh, that's it. That's for you.
yes.
Yeah. Okay. Yeah, but for the, I mean, if you take the file, yeah, you can call. Yeah. Yeah. No. Just do it very good. I mean, the only thing Honda is the jack. All right. So remember, only we made a distinction for A when we are trying to find the fundamental matrix or the exponential matrix. But when we write down, when we assume the existence of the fundamental matrix, we don't care whether A is constant or not, correct? Because we're assuming phi is a constant, is the fundamental matrix, all right? That's it. So let's assume that. So here is A is an n by n matrix, and G is an n by 1 vector. They're all continuous on some interval I. Okay? So if we know the fundamental matrix, solution phi of t of x prime equal ATX, then we can write the general solution, and this is gonna be 3.31, and this is 3.32. Then we can write the general solution of 3.31. You see what happened? Okay. All right. So this is what we are gonna do. So we're gonna assume and so forth. All right. So here is what we're gonna do. All right, so this is definition 3.3.1. Let XH be the homogeneous solution. This is X lower H of 3.2. If XP is a particular solution of 3.31, then the general solution of 3.3.1 is X equal XH plus XP. So you know the homogeneous solution of that, you know particular solution of that, and then you add them, and this is the general solution. Okay? So read this and dwell on it for a second. All right. Now, we have seen in the previous theorems that is phi is a fundamental matrix solution of 3.32, then phi k is also a solution, where k is an n by 1 vector. It's like a C, okay? All right, I'm gonna state a theorem next, and we will prove it. We will show it. And now we're gonna assume here xt naught equal x naught. So we're given an initial condition. All right. I'm gonna flip the board. I'll give you 1 minute before I flip. All right. Okay. That is theorem 3.3.1. Let phi of t be a fundamental metric solution of 3.32. Then x of t is a solution of 3.3.1 on I if and only if x satisfies x of t equal phi of t, phi inverse of t naught, x naught, plus t naught to t, phi of t, phi inverse of s, g of s ds. Okay? Any questions? Well, this is if and only if. So the proof. Suppose x of t satisfies, this is 3.3.4. Suppose x of t satisfies 3.34. We show it satisfies 3.3.1. So all I have to do is, first of all, x of t naught equal to phi t naught, phi inverse of t naught, x naught, plus t naught to t naught, and that is I x naught plus 0, and that is x naught. So first of all, it satisfies the initial condition. Okay? See what I did? Because x satisfies 3.34, we need to show it satisfies 3.31. And remember what 3.31 is. X t naught equal x naught, and it's this one. So we verified this, we still need to verify this one. Okay? And if this is if x is given by that. Now, x prime of t equal phi prime of t phi inverse of T naught X naught plus phi prime of T, T naught to T, phi inverse of S, G of S, ds, plus, this is a Leibniz rule, plus phi of T, phi inverse of S, G of S. Okay? Recall, del over del T of something from T naught to T, K T S ds is K T T, when you put T in, a plus T0 to T del over del T of K T S ds. This is called the Leibniz rule. So this term here, this term comes from replacing S with T. You see? Oh, this is T, sorry. T, okay? So this is called Leibniz rule for differentiating integral. All right, so this is equal to X naught. This is X prime of T, so I'm not done yet. Phi prime of T is what? That is, so X prime, phi prime is AT, phi of T, phi inverse of T naught, X naught, plus AT, phi of T, T naught to T, phi inverse of S, G of S ds plus G of T. You see what happened? Because phi is the fundamental matrix of the homogeneous, so that means phi prime is A phi. All right, I'm gonna erase this here. And this means X prime is factor A out. And then you're gonna get phi T, phi inverse of T naught, X naught, plus T naught to T, phi T, bring phi T in, phi inverse of S, G of S ds, plus a G of T. But what is X? This is X by definition, because we said suppose X satisfies 3.34. So that is X. So that is A xt plus gt. We're done. Okay? Any questions? All right. Now the opposite. Now we're gonna show if x solves 3.31, then x is given by 3.3.4. Okay? All right, so we know xh equal to phi of t to some vector k, and we're gonna assume xp equal to, okay, we're gonna assume that xp is equal to phi t ut, where u is to be determined. Okay? So, hence, xp satisfies 3.31. Then what is xp prime? Xp prime is phi prime of t ut plus phi t u prime of t. Okay? So substitute xp prime into 3.31. If we do that, we're gonna get phi prime of t ut plus phi t u prime of t equal to at x. Xp is phi t ut plus g of t. Okay? All right. Are you all with me? Now, this is at phi t ut plus phi t u prime of t equal to at phi t ut plus g of t. So this and this cancels out. It's zero matrix. And then we get phi t u prime of t equal to g of t. Since phi is non-singular, we have u prime of t equal phi inverse of t, g of t. Now we're looking at, so integrate, and we get ut equal t naught to t phi inverse of s g of s ds. We're assuming u0 is 0. Okay. Now I can erase this. But xp is phi t ut, which means it is phi t naught to t phi inverse of s g of s ds. Finally, the general solution of 3.31 is x of t equal xh plus xp. That is phi of t times some vector k plus phi of t naught to t phi inverse of s g of s ds. Okay, now we're not done yet. So the question is, what is k? Well, since x0 equal x of t naught, we have put it here. X naught equal xt naught equal to phi t naught k plus phi t naught to t naught phi inverse of s g of s ds. Because I'm computing at t naught. So what does that mean? That is equal to phi of t naught k, because this is 0. This implies x naught equal phi t naught k, which means that k is phi inverse of t naught x naught. Okay? Well, we're done. But put k here. Hence, x of t equal phi t. What is k? Phi inverse of t naught x naught, and then the other one is phi of t naught to t phi inverse of s g of s ds. This complete the proof. Okay? It's beautiful. Beautifully done. Any questions? Any questions? All right, I'm gonna stop here and we'll do next time an example. So to get ahead of me, if you wanna read example 3.11. I'm gonna log out if you don't have any questions. Okay.